Thank you very much, and it's quite an honor to be able to present what we're doing, what RIKEN is doing. So this is a talk, my talk. I'm the director of RIKEN RCCS. I'll give you a little detail of the center. We're basically a supercomputing center, a national supercomputing center, and this is the talk that I'm giving, but also the new division director within RCCS, Mr. Sato, provide a lot of the materials. Okay. So firstly, who are we? Well, we are one of the 13 centers at RIKEN. Of course, RIKEN is the flagship national science institute in Japan, national lab. And there are 13 centers in RIKEN, one of which is us. One of our sister center is a center led by Nakamura-san, who heads the RQC, the Quantum Center, and but we're the HPC center. And what we do is basically push the envelope of computing. So we say the science of computing, by computing, and for computing. The science of computing is basically computer science for the high-end computing. But unlike many of the computer science departments around the world, we also put a lot of emphasis on using the results that we obtain from the research onto solving the most difficult problems in other domains of science, like climate, like materials, like life sciences, manufacturing, etc. And then there's a science for computing, other scientific disciplines that contribute to the advances of computing. And for example, neuromorphic computing, which of course gave birth to AI, and also quantum physics, which gave birth to quantum computing. So we partner with many of those institutions and companies and so forth to utilize those new modes of computing. So, and the collective synergy between the three allows us to advance computing to the next generation. We don't just do research, but we also use the output of research to build some of the world's fastest supercomputer. That's a national flagship supercomputer. This is the current incarnation. This is Fugaku, which we had been working on since 2010. The predecessor was a K computer, which was a flagship supercomputer for Japan. In 2020, we designed and built the new version, Fugaku, in partnership with many companies like Fujitsu and also the entire HPC community in Japan. So Fugaku is still one of the world's fastest and the largest supercomputer in the world. It occupies about 3,000 square meters. It has 432 cabinets, 158,976 nodes, which run in parallel. Fortunately, programming Fugaku is easy. For one thing, the processor we developed with Fujitsu is a high-performance ARM processor. So the internal microarchitecture is our own, but it will run exactly the same program as your smartphone or ARM-based PC. Okay. So one uses about 60 megawatts in production, or about 20 megawatts including cooling. Of course, we can go up to 30 megawatts. And but one of the most important aspects, if you consider simulating a quantum computer on this machine, is the fact that it's got about 5 petabytes of memory with about 163 petabyte per second memory bandwidth. And as I will allude to later, state vector simulation, the quantum computer, is largely bound in terms of qubit size. In terms of size of qubit, you can simulate by amount of memory. In Fugaku, state vector simulation can go up to about 50 qubits. But also the speed of simulation is largely governed by the memory bandwidth, which is, again, about more than 100 petabytes per second. So, Fugaku can be used as the fastest state vector quantum simulator in the world. In fact, we have applications that do that. Yeah, but I'll talk about that later. So for the spec geeks, computer spec geeks, here are some of the very large scale overview of the machine. It was it was number one in most categories. It still is number one in those various supercomputing rankings, like HPCG, HPL AI I'm sorry, HPCG, Graph 500, etc. It won various awards like Gordon Bell Prize, and it's supplying about 1.3 billion node hours, or about 60 billion CPU core hours to research, not just Japan but globally. And we have quite a bit of collaboration around the world, including those in Singapore with like H-Star and SEC. So people in the audience, most of you researchers, you're completely eligible to apply for time and use Fugaku. Okay? And this is very important, as Fugaku will be one of the centerpieces for the Quantum-HPC hybrid infrastructure we have started to construct starting this month. Okay, so but those numbers, as scientists, engineers, we typically get infatuated with numbers. Of course, that's our bread and butter. But the important thing is not so much, the important factor is not so much the numbers, like flops or bytes per second or number of qubits, but rather what problems we can solve. What are the scientific problems we can solve? And of course, Fugaku was not designed to be number one in the world. It was designed to solve problems, scientific problems. And there are many application areas that were, and in fact, applications themselves that were developed in concurrence with Fugaku's development that lasted over 10 years. And these are areas such as health and medicine, disaster prevention, climate, long-term climate change, things like energy, carbon neutrality, including generation, transmission, storage, things like the industrial manufacturing, from materials all the way up to very big structures like cities, airplanes, and so forth. And of course, basic science is important as well. So Fugaku's development not only consisted of developing the hardware, but developing these sciences to utilize these very, very large-scale systems to innovate and, again, solve some of the most challenging problems that encounter mankind. Okay? And that's what computing is. Computing is has now become the fabric of the society. And in high-performance computing, we have always, and more acutely, as HPC, high-performance computing, has become the instrument to advance science. That to solve these societal problems, important. In fact, Fugaku's development goal is not to become number one in various metrics, but to achieve tangible speed up sufficient to innovate in all the areas of sciences that I've talked about and more. So the objective was to achieve almost 2 orders of magnitude speed up, which will lead to this quantitative, not only quantitative, but qualitative change in the sciences and we do and the problems we can solve in all the areas. And in fact, we have achieved, that was the goal. That was a national goal, and we achieved that by achieving almost 100 times speed up in all, in all of the areas. Okay? And something like this is important not just for the various areas we know about, but when we have societal crisis like COVID, we're finally recovering from. Now, I can travel to Singapore freely, but 2 years ago I couldn't come to Singapore because Singapore is closed, and people in Singapore couldn't get out of Singapore, right? Which was a very hard time. But all these application areas, many of these applications, those top-end applications that will scale to the entire Fugaku, like more than 100,000 nodes on Fugaku, were directly repurposed to solve COVID problems, regarding COVID. And from things like very deep down analysis of the molecular structure of COVID spike proteins in order to assess the is how various structures would have very different bonding characteristics to the human targets, to various other types of more macroscopic analysis of what would happen, if someone coughs and emits aerosol, to what are the economic impact, if you do a lockdown, depending on various policy of lockdown, what will be the economic impact. So all the way from atomic, even quantum levels, all the way to societal levels, there were many projects that were launched on the very early days of Fugaku. In fact, one of the, and these were very effective. In fact, one of the aerosol simulation we had done had won what's called a 20 Gordon Bell Prize, which is the highest accolade in one of the highest accolade HPC, because we were able to repurpose one of the most powerful CFD computational fluid dynamics application we were developing for Fugaku, and we purposed that entirely to deal with the COVID transmission. Okay, so how if someone coughs, he or she would spit aerosols or sing karaoke or whatever, and then and the societal situations from classrooms to auditoriums to riding a taxi to flying on airplanes, being karaoke boxes, whatever. How these transmissions occur, not just outside your body, but also from internals of your body, and how these infection risks can be mitigated by various means. How can we quantify this drop in the transmission probability so as to reduce the risk and allow the society to function normally? So we create more than 2,000 digital twins signifying various societal situations, and did for the first time, did very detailed end-to-end simulations of how these transmissions occur and how they can be mitigated. Okay, and this really helped to solve lots of problems, and allow Japan to stay fairly open during COVID, not suffer total lockdowns like some other countries, allowing our GDP to suffer much less, hundreds of billions of dollars less downturn in economy due to less restrictive lockdown. Okay? So that's what HPC does, and our new effort is to try to extend that to all realms of science with new computing paradigms such as AI and such as quantum. So RIKEN has this so when the new President Konokami came, he launched a project called TRIP, which is Transformative Research Innovation Platform. It's basically to create a digital platform to really advance science beyond what individual scientists do today. So to basically create a digital platform consisting of various types of new massive data acquisition, new computing paradigms, and also new computing infrastructures. So we have embarked on this since last year, and various centers which are pertinent to computing, like our center, Nakamura-san Center, our AI Center, our Applied Math Center, and also various application centers, like centers with respect to biology, also instrumentation, like our Spring Gate. They all are part of this big project, TRIP project. And now, so with respect to our center, because we do core computing, we research and also build. We do research on and also build up this computing infrastructure. We have largely three directions. One is, of course, to push on with the current supercomputing towards so-called, whatever you might call it, Zeta scale. So we're since Fugaku's now done, of course, we're operating it. We are also embarked on a journey to advance it further by order or orders of magnitude. And so right now, Fugaku, we're looking at what the next generation machine would look like, with partnerships with various companies, now with various US companies like Intel, NVIDIA, AMD, HPE, also, but of course, with Japanese companies like Fujitsu and also many other partners to see whether we can make another leap in computing performance and thus achieve these qualitative changes in the sciences that we can do to impact the society circa somewhere around 2028 to 2030 timeframe. So that's an ongoing thing that's I'm deeply involved, and it's become the main project. We also have a new effort in AI, AI for science. And we're, again, not because AI is a big boom, we've been doing AI for some time for applying to science. And now RIKEN has a new project, RIKEN AI for Science, and we'll be partnering again with various institutions like Argonne National Labs. They're formulating what's called a trillion parameter consortium to build these models for science consisting of GPT-4-like size models, but more tailored for science, and also be able to do various types of inference tasks with these predominantly generative AI to advance science. And it's a big effort, and we are, again, one of the centerpieces, especially on the computing infrastructure side, and also combining simulation, classical simulation with AI methods. But today's talk will focus on the quantum and quantum third effort, and one of the most exciting effort is to try to combine traditional HPC with quantum computing. And there are multiple efforts in this area, and in collaboration with our sister centers like RQC and other institutions. But our main objective is to build, just as we have built supercomputers to solve the hardest societal problems. Can we build at this point, or maybe several years down the future as quantum computing, and of course classical computing evolves, how do we build infrastructure? I mean, what are the infrastructures that are needed to allow for people developing quantum algorithms, quantum applications, and typically these are hybrid HPC and hybrid classical quantum. But how can we help to advance that by building a formidable infrastructure that allows for ease of access to the top supercomputer and top quantum computer of the world? So we've just been funded for this. It's about $140 million over the next 5 years to facilitate an infrastructure. Okay, so it's not our role to build our quantum computer ourselves. That's not Nakamura-san's job. But it's unlike in Fugaku's case, we built the system our own. But in the case of quantum, it's our role to build an infrastructure, including the software, to facilitate this platform to be used by scientists in industry that are wanting to develop such a hybrid algorithm. So just as a reminder, so RQC builds quantum computers and work on various new methods, not just cryogenic like Nakamura-san's working on. They're working on things, photonics. They're working on silicon, various methods, and we're more the platform. In this case, we're doing more the platform work. There are other centers that are working on the underlying mathematics and also things like quantum AI. Okay, so in order to facilitate this, we have many researchers, both in computer science, also in the applications. But if you see in the middle, we have just last April, we have created internally a new Quantum-HPC hybrid platform division within the center. And the division director is Matsuoka Sato, who's also the deputy director of the entire center. But we will have people who will be working on the software, we'll be working people on the simulators, and we'll have people working on the infrastructure to facilitate this hybrid facility. So to be very exact, we currently have 3 units. One unit, or this team, will be looking at what's the software environment, what would the software environment look like to allow for people who are wanting to develop these algorithms to utilize. So what are the essence, what are the software do we need to develop? For example, you might have a supercomputer, you may have a quantum computer. Right now, these two are being developed or facilitated as individual entities. But we know if you ever use a supercomputer, you know it's like batch-based. So there's no easy way. Let's say you have Fugaku. Let's say you have a quantum computer, and you want to run some variational algorithm. Okay? There's just no easy way to do that on the current infrastructure, because you cannot co-schedule a quantum job and an HPC job at the same time. There's no mechanism to do that. Okay? So we need a software mechanism to allow for these variational, because you're not running on a PC. In both cases, both on a quantum computer and on a supercomputer, these two are scheduled differently. They have different characteristics, so you need to have them co-scheduled so that your variational algorithm will work. How do we do that? There's no infrastructure to do it. So that's something we need to build. We need to have enhanced our simulation capabilities. As much as there's strong expectations that we'll have a 1,000-qubit machine very soon. Of course, when people will want to develop algorithms, they will rely a lot on the simulator. Okay, so how do we enhance our ability to do much bigger simulations of these quantum computers? Because of course they are fundamentally error-free. Or how do we enhance our simulator to simulate some of the errors that are occurring in the system so that we can run effective, let's say, develop error mitigation algorithms? How do we operate these two machines? Usually the quantum computers have been developed, the cryogenic machines, to be standalone. They sit in a very different environment to a very large machine like you saw, Fugaku. Okay? These have different types of cooling requirements. How do you connect these two machines? Right. What are the facility requirements? So we need to look at those in order to facilitate a very large-scale quantum platform that allow for these types of algorithms to be developed. So we're involved in various projects, but again, I'll focus mostly on this hybrid platform project. We also, a lot of our researchers who have some joint appointments with people, like RQC, for example, they're working on a little bit higher level things like some of the applications of quantum, but I won't talk about that too much today. But nonetheless, as you can see, we're involved in multiple projects, but one of our principal action item is to develop these platform. But what do we need the platforms? Well, because you've seen this, right? You've seen the various, even this. I mean, Fugaku runs tons of different types of applications, many types of applications, but even this particular COVID example, you'll see that they span from various at the very low, I would say, microscopic level, doing quantum chemistry simulations, all the way up to societal simulations. And what the expectation, especially in the material science or even like nuclear physics and those types of areas, we're really starting to see the limits of our ability to simulate these types of systems. So things like CFD, it's okay, because we are, these are things which I will allude to later will likely not be accelerated with quantum. Rather, these are low-order algorithms, order n, or even constant. or the root n. So things on the left-hand side, which are very much bandwidth-centric, again, like CFDs, things like structural mechanics, many of machine learning, although not all of them, algorithms, especially inference algorithms. These are mostly bandwidth bound. So we have no expectations these will be accelerated by quantum. Okay? That's the reality. However, as the complexity increases, we have some areas that will become very hard, going from order n to order n log n to order n squared, and all the way up to exponential, or of course NP hard, which is even tough for quantum, but still, but it's very, very difficult for conventional machines. So as the computational complexity increases, we expect that because of the this utmost difficulty in areas like quantum chemistry, again, things, nuclear physics, and in some areas like cryptography and so forth, we expect that we will not be able to increase our capabilities much further, and rather, we should try to have a quantum future, or the non-quantum futures for these types of applications that would be too challenging for conventional computing. Well, that's what quantum computers is promising. But then the question is, how do we then accelerate the development of algorithms on the right-hand side? Also, how do we try to find out how do we partition our system? Because, for example, in sometime in the future, while I'm still active, I'm hoping that some of the most challenging quantum chemistry problem can be solved by using quantum computers, which I know is challenging, but suppose we can do it. So the dominant algorithm used in those cases is a very numerical algorithms have very high, extremely high computational complexity, n to the fourth or n to the fifth, or even exponential. So those, and also they require high precision. It's not just the computational complexity. Typically, these computational chemistry apps, algorithms require support of something like FP64. Some people even demand things like FP128, which will be an increasing minority as the world is infatuated with AI. With a lot of, as many of you might know, the world of AI is now moving to lower and lower numerical precision, like FP16, bfloat 16, FP8, FP4, 6, FP4. Even to the extent that it will, they just do full quantization to be like 1 bit, but just exponents. So with that trend for lower and lower precision, and also many applications are bandwidth bound, where quantum computers good at, hopefully will be good at, is direct opposite to how the classical computers will develop. Okay. So if that region can be covered by quantum, then that's great. In fact, then we can throw away FP64 and leave it to quantum computers to solve that. Then we can optimize the classical machines to do that, to be bandwidth bound, to deal with bandwidth bound problems, or to deal with mostly AI. Whereas quantum computers can concentrate on this specific application area. So that's what we're foresee. But again, how do we accelerate algorithm development in the sector? If you remember COVID, especially it's in that region, the fragment molecular orbital calculation, for example. That's our data, that we have high expectation that in the future will be accelerated by quantum. Everything else, there's no expectation, but that one that area, which is very important, we have very high expectations that there will be acceleration through quantum. Okay, but then how do we do that? Well, we can say we'll just attach to the machines, but of course we need machines with thousands of virtual. I don't have to preach to the choir. There's been lots of analysis done with this, like how many qubits you need to solve particular algorithms, and you need reliable qubits. Blah blah blah. I don't want to go too much into details because we all know this. But what we need are algorithms, and there's a paper which is very controversial to this date, published at CSCM. Of course, a claim made in the paper by people at ETH, like people like Matthias Dreyer and Thorsten Hoffler, is that one would need exponential speed up compared to a classical algorithm. So Shor's algorithm is good because it's exponential, but Grover's algorithm is not useful because it's only quadratic. And they have gone on to prove that. Of course, I know there are lots of controversies, but if we pit this against the requirements, right, of the algorithms on the very right-hand side, in which we do expect exponential speed up, because these are like HSP, NP hard, or at least an HSP type of problems. So how do we come up with algorithms that will exhibit exponential speed up? Not like Grover's, right? Which we're not very, us in HPC we're not very interested in, because it can be covered by classical systems. So we need more exponential algorithms, and algorithms that exhibit exponential speed up. And we need people to develop these, but in order for people to develop this, and in many cases, some of these algorithms are hybrid. Like we need not only to develop the algorithms, but try to apply it to real sciences. And it cannot just be algorithms on paper. For example, there are things. When you look at the textbooks or look at any of the papers, there are claims like HHL, which is a quantum, many would know, which is a quantum algorithm for linear system equations, which will seemingly exhibit exponential speed up. But if you look at the fine details, these are the conditions that the algorithm exhibits speed up. Exponential speed up is when you have, for example, very small condition numbers. And that's a trivial problem to solve. If the condition numbers are small, that's a trivial problem to solve on a classical machine. Okay? So although it's exponential speed up, there's no use for it because it's not useful. So we believe solving linear equation will not be used. Quantum computers will not be useful. But if there would be use, it needs to do that with like ill-conditioned problems, right? With very very big condition numbers. But so far to date, no such algorithms exist, as far as I know. So we need people to be challenging this, and that's why we're building infrastructure to allow people to challenge. Not for us, well, or some of us to challenge, some of the people in RIKEN to challenge, but also people in the community to challenge. And that's how supercomputers came to be. Because there are lots of algorithmic challenges, application challenges, science challenges, but the reason we were able to solve them is for force people to try very hard to develop new algorithms, but also the fact that there was a platform to immediately apply these innovations to solve real problems, as you have just seen, like with the COVID example. So that's what we're building today. Okay? Now, when we look at try to combine classical and quantum, there's typically what you see like on like Amazon bracket and so forth is very much coarse grained. So you have a quantum computer, you may have a classical computer, sometimes a supercomputer, but they're very loosely connected, let's say over the internet. And for some quantum computers, this is fine. Like, for example, if you have ion trap machine, the cycle time is very slow. So very slow and comparable to the latency you experience on the internet, which is in milliseconds. But if you look at ion trap machine, their cycle time is also in milliseconds. So it's well matched. But some other supercomputers, quantum computers, I'm sorry, like cryogenic machines, the cycle time is very, very fast, like in hundreds of in like 10 to 100 microseconds. So for that, we need much tighter coupling. And of course, if there's things like error correction, you may need even further tighter coupling because you need to go into the machine. So, so that's why for looking at the machine, and then looking at the algorithms, like a lot of the variational algorithms, tighter coupling may or may not help. It may help, it may not help, but we believe that if you couple this with things like error mitigation, it may help. So for those quantum computers with very fast cycle time, it's best it's co-located with a supercomputer. For some quantum computers with very long cycle time, it can be placed over the internet. So we need to figure out how we would do this, and try to develop these important algorithms. Okay. And also, tighter coupling, like I said, is important for when we offload parts of the simulation over to supercomputers, because it may involve the whole algorithm may not just be variational, but there may be some sort of divide and conquer type of algorithms where certain parts of the algorithms are calculated in a classical computer and some parts are calculated on a quantum. Now we have some work in quantum chemistry trying to do that, where depending on the location, depending on what the force field is, looks like there's advantages to classical, there are advantages to quantum, and try to combine both may be a good answer. So we need to have, basically we need to have tangible machines with tangible number of qubits, but we need to be able to have have qubits that go beyond what users can do on PC, but rather be able to have real machines that will have simulators that go well beyond PCs, be it state vector or tensor-based methods. And then, of course, have real machines, which may be NISQ machines for the time, but also have sufficient number of qubits such that they go well beyond what can be simulated on a user's personal environment. And like I said, in terms of error mitigation, there are some studies that pointed out when you have very large number of qubits, you may need a supercomputer to do error mitigation. So, and also in order to how to build these very large systems, there are a lot of work being done to do some combination, like cutting and knitting, so-called cutting and knitting, in order to combine smaller quantum computers to effectively arrive at large number of qubits. But again, hard to massage these quantum computers, multiple quantum computers, and conduct error mitigation or even ultimately error correction. You may need a very large supercomputer to do that. So for various reasons, you need a very tighter coupling of very large scales, preferably top of the line, world's leading supercomputer and the world's leading quantum computer. and world's leading simulator. And that's what we're doing. So, there are some work, like in Europe, where quantum computers are being facilitated in supercomputing centers, but we're trying to go a step ahead and try to have the top supercomputer and a top quantum computer and top simulator, all of them at the same time, and then have layers to combine them, have software layers to combine them. So it's not your 10 qubit machine hooked up with a supercomputer. We want a supercomputer that's quantum computer that's state of the art, which right now is hundreds of 100 qubits or more. We want simulators to be capable, right? Again, be able to simulate very large system. Of course, depending on the system, you may be using state vector or variations of tensor-based algorithms. But again, we want top performance in simulating of that. And of course, the supercomputer, we want the top machine. And we want the users, and then we want the users to be able to look at the platform as if it's all uniform. Right? You don't have to have different accounts. You can have a single account. You can log in, same software stack, you program in Qiskit, Cubo, or something above. Run your algorithm, run ubiquitously across different machines, different simulators. You combine with multiple types of supercomputers, top ones, etc. From a user's perspective, it's a single unified environment. That's what we are aiming to build. We will be hooking up Fugaku. We will have a mid-tier GPU system to serve both as alternative type of supercomputer, also to be able to run mostly tensor-based simulation, because Fugaku is much better at doing state vector simulations. The GPU system, we were thinking maybe not too big, because we don't have that much money. Maybe like 1,000 GPUs or so. Okay. Not too big. And then we'll have a real quantum computer, which is commercial, and I can't reveal to you the name of the vendor right now. We may be able to do so next month, but this will be more than 100 qubit machine. But for the first time, it'll be facilitated directly next to Fugaku. Well, next to, not on the side, but actually on a different floor. But it'll be tightly connected with Fugaku using very fast network. And then over the internet, we will be connecting other resources. There will be ion trap machine in RIKEN Waka, which is about 600 kilometers away. But because, like I said, because these ion trap machines have very slow cycle times, it's fine to connect them over the internet. Right? And then, of course, we'll be working with RQC. We have some POC out to hook up Nakamura-san's machine as well. And then we'll have other collaborating universities, like University of Tokyo, their supercomputing center, Osaka University's their supercomputing center, and of course, people like Fujii-san to facilitate this infrastructure. So then I'll get to some of the details for the remaining part of the time, but in the interest of time, I will try to be very succinct on the simulator part, because then I'll try to focus more on the software piece. Just to give a highlight of the simulator, we really want to increase the state vector capability up to the point when we saturate the memory of entire Fugaku, which is about 5 petabytes in total. So with that, we know that we can simulate up to about 49 to 50 qubits. But there are two problems, of course. We need to increase the number of qubits as much as possible by compressing by using essentially compressing the data as much as possible. But also, this type of compression and also algorithms are very, very important, because the entire simulation per cycle will be memory bound because we're moving all the bits around, basically, to emulate all the states of the quantum system. And this will take enormous amount of memory bandwidth. So we're not bound by compute. Just like computational fluid dynamics will be bound by memory bandwidth. Good news is that Fugaku has one of the highest memory bandwidth, has the highest memory bandwidth of any supercomputer in the world. This is very different from from the tensor-based methods, where if you do straightforward tensor-based, any sort of tensor-based methods, these are more or less compute bound. So that's where things like GPUs and their capacity for being able to emulate AI to basically speed up AI using the matrix engines like tensor cores on NVIDIA has the advantage. So that's why we're facilitating the GPU machine, because they're much faster in terms of doing tensor-based simulations, but may not require that much memory. Whereas on Fugaku, we'll be focusing more or less on the state vector, although of course we'll be doing tensor-based methods too. So on these machines, typically each cycle, this is a 35-qubit simulation kit that was done on a previous machine, K computer. So for the most part, because they're bound by memory, each cycle takes about a few seconds. And we're trying to speed that up substantially with Fugaku. I won't go into details, but also increasing the number of qubits, which will, of course, then the bandwidth requirements will increase. So the goal is to preserve this cycle time while increasing the number of qubits, and we have largely achieved that. Nobuyasu Ito's team is working on this, and we have very stable speed up to 40 qubits and up to about 50 qubits with very, very fast cycle time. Of course, they're working on increasing this technology more by going to improving on their algorithm and also working to reduce the memory bandwidth, especially to increase the circuit depth. That's where we really want to use this state vector implementation when we have very deep circuits. So they're working on various optimizations to allow for where state vector simulations will excel most when you have not wide but very, very deep circuits, and then but to optimize the memory bandwidth such that we can emulate the very large, very, very deep systems. Now, in terms of software, the system software, we are trying to construct a common runtime where we have a supercomputer with various simulations and also running classical tasks. We have a quantum computer. Sorry, let's get the pointer here. And then we have a quantum computer task. So these are managed. These tasks are managed with the resource managers. And then we have what we're building is called a quantum computer procedure call library to be able to call these resources. Also, these resources need to be code scheduled because we're going to, in the variation algorithms, or any sort of hybrid algorithms, they'll be used at the same time. And then we'll have some common API, and we expect that things like Qiskit or Kibo, things called a programming middleware, will sit on top of that. And of course, there are other details like how do we do like circuit knitting? This will be much lower stuff, so we'll be supporting CASM and try to combine that with circuiting supercomputers, which will be a more low-level thing. But yeah, I can't speak about all the details today. But largely what the users will see is here. But all the differences underneath, including these types of code scheduling, will be buried in the software stack. So yeah, so that's the large overview. And since I'm running out of time, I'll skip most of the details. But so users will be able to submit a hybrid algorithm, to construct a hybrid algorithm, submit it to the system, and then the system will take care of which machine to schedule, be it the real machine or the hybrid or the simulator machine. It'll also schedule a job to the classical system together. They'll be co-scheduled. And then, of course, the users will be able to federate within the program, because within the program or groups of programs, there'll be a workflow that will call the classical computer and quantum computer, but at the top level, we are creating a remote procedure call type interface such that the different types of tasks that we co-scheduled on both machines can be federated into a single workflow. Okay? So that's how we expect people to program. And again, more details will be published, but basically, people will be able to have a program and schedule. The resources will be scheduled for you, and all you have to do is to call up different types of modules you have created. Let's say in Kibo, and to be able to call them and federate them, put them together into a cohesive, let's say, a hybrid algorithm. Okay, skip. Okay, so that's what we're doing, and hopefully, and of course, the machine for the first couple of years or so, we'll be very busy constructing the system, but we're looking also for collaborators, because what we want out, what we're required, what we want, and what we're tasked to do is to, if not just to build the platform, but to come up with tangible applications. May not tangible in the sense that it may not be something like on a traditional supercomputer that will solve societal problems immediately. That's something that our funding agency is not hoping for. They're very realistic, but something that will indicate if, as a POC level development, new algorithms, new methods, where if we continue on the trajectory of increased number of qubits, increased fidelity, increased capability, better coupling, that down the road, not so far distant future, but in the near future, there will be services, especially in the area where exponential speed up is required to achieve these tasks, which will not be achievable using traditional computers, but to demonstrate that such things, such services will exist. So, so we welcome collaborations, and and thanks very much. We'll hope we can build a very bright quantum future. Thank you.
Thanks for the talk. Questions?
I do have a question.
Yeah.
Since I have the mic. You were mentioning some application of the supercomputer that are trying to explain environmental aspects and maybe fighting climate change. Can you maybe elaborate on that and tell us if you envision that quantum computer can help in this area too?
Can you repeat the question again?
Yeah, you were mentioning at some point all the applications that the supercomputer is used for. So there was some application in medicine, some application in chemistry, some other stuff, and there was some application in environmental aspects. Can you elaborate on that, please?
Yeah, I mean, there are, not just us, but there are various roadmaps associated with like how many qubits and which areas. So like in, like nuclear physics and so forth may be, the low bar is lower. But of course, the biggest expectation is in material science, especially with substances that require exponential capabilities in terms of having large systems and so forth. Microsoft typically says, how to find something alternative to Harvard-Bosch. So that's, in particular, material science would be one of the biggest target area, we believe. We know it's very hard, but things like catalysts, especially catalysts, there's very high expectations that at some point this will become, there will be some innovations in various fronts. Because like I said in my chart, my pictogram, that's the area that will very likely not be possible for classical supercomputers to achieve sufficient speed up to solve these problems. So, Yeah, so there's expectation. And if we do that, then we can actually relieve the supercomputers to be built to try to accommodate these types of applications. So there can be optimizations on both sides. Quantum computers serving as the de facto accelerator for certain types of problems, especially in material science, hopefully. And then the classical computers optimized so as not to excel in that area. In fact, we're starting to see that already as the effect of proliferation of AI. And because the proliferation of AI says material science skills would be heavily compromised. Yeah.
We have time for another quick question. Yep.
Hi, thanks for an interesting talk. In your presentation, you made this clear separation between algorithms with exponential speedup that are useful and polynomial speedups as being perhaps not so useful for practical applications. But there are some studies.
I'm sorry, it's very difficult to hear up on the stage. The acoustics is horrible here. So can you
right,
speak up?
I can just repeat that. Yeah. You mentioned in your talk that you made a separation between exponential speedups being practically useful versus polynomial ones that may not be useful.
Yeah.
But there are some resource estimates that indicate that perhaps polynomial speedup that is beyond quadratic can also be useful. I just wanted to know your thoughts about that. Have you seen this before?
Yeah, I mean, I said it's debatable, so of course, Torsten Hoffler is my collaborator, so I'm a little bit more favored towards having exponential, trying to achieve exponential will be more of what the advantage that quantum computers will exhibit no matter what. Okay? Because polynomial speedup is very, very delicate in that, of course, we read those papers, and if you look at other papers that other people have written, it's an area for realistic problem sizes can be easily be caught up. Now, now having said that, if you find a particular real application where with some like quadratic speedup, like polynomial speedup, where there's just no way we can build a supercomputer, realistically build a supercomputer, by the way, which is really large nowadays. That it's still unable to catch up because of the constant factor that will be inherent in the algorithms. But right now, as far as I know, there hasn't been a demonstration for real problems. Any sort of a polynomial speedup will not be overtaken on a quantum computer, will not be overtaken by classical if you build a machine that's realistically big enough. Yeah, so it's a challenge. So again, I said this is debatable. The challenge is to find a real problem where you say, no, there's just no way, although it's polynomial, there's just no way you can build a machine that's big enough because the machine will be like gazillion processors. Right? And then that's not very realistic. But remember, Fugaku has 8 million CPUs. So the constant has to be very, very large.
Let's thank our speaker again then.